Okay, so this is objective 11.1b, and these are the double angle identities. And it's tagging on to 11.1a because you use the sum identities to build the double angle identities, so they're related. Yes, sir? What? Oh, okay, thank you. And so our essential questions are how do I derive the double angle identities from the sum identities? Really important in calculus for you to be able to take one formula and transform it into another formula that's a little bit quicker to use, possibly. Deriving happens a lot, finding derivatives in calculus all the time. So it's skills that you need to build. So you're going to derive, and we're also going to be using our trig function, SOHCAHTOA, in conjunction with the double angle identities to solve some problems. All right, so we're going to start with a statement that the double angle identities can be derived from the sum identities. And that just means I'm going to take the formulas for the sum identities and transform them into double angle identities. So multiple angles again in this situation, multiple angles. But this time your angle, the angle that you're talking about is just the angle plus itself, or the angle times 2. So if I was going to say that the sine of theta, let's say it's the sine of 60 degrees. Well, the sine of double 60 degrees is the sine of 120 degrees. So you're doubling the angle. So let's see if some things make sense. So I'm just going to grab up my pencil here, and I'm going to ask you a question. Is it true that 2 alpha is equal to alpha plus alpha? Is that true? Right, combining like terms, just consider alpha as a variable like x, and that's definitely true. So what we're going to do is, here's a double angle identity, and what I'm going to do is I'm going to take the formula for the sum, the sine of a sum of 2 angles, the formula, and I'm going to derive the formula for the double angle. Looks like this. So we're going to say the sine of 2 alpha is the same as the sine of alpha plus alpha. It could be theta plus theta, x plus x, anything I want to be the placeholder for my angle. And then we're going to use the formula for the sine, a sum of 2 angles. And that goes like this. Sine of the first angle, cosine of the second angle, plus the cosine of the first angle times the sine of the second angle. Right? That's the formula we learned yesterday. Please remember that I can rearrange this to say sine of the first angle, cosine of the second angle, plus the sine of the second angle, cosine of the first angle. Can I not rearrange this to also say sine alpha times cosine alpha? True or not? Yes. Multiplication is commutative, and so I absolutely can do that. So let's simplify that. So that's our sum formula. Let's turn it into the double angle formula. So if I add those, since they're like terms, that's 2 sine alpha cosine alpha. And so if I had my highlighter at this point, I would indicate that the sine of the double alpha is equal to, not all that stuff in the middle, we're just deriving a new formula here of 2 sine alpha cosine alpha. So that, what I circled or I put a box around in red, will go on your trig identities index card under the double angle identities. I'm sorry, the double angle identities. Got it? Questions about that? Any questions how I got from sine alpha cosine alpha plus cosine alpha sine alpha to 2 sine alpha cosine alpha? Any problems with that? No? Okay, then let's move on to the cosine of double alpha, or 2 alpha. I can apply the same logic that I applied with the sine example that I just did. I could say that the cosine of 2 alpha is the same as the cosine of alpha plus alpha. True statement. And I know something about the formula for the cosine of sum of 2 angles. And that looks like this. The cosine of the first angle times the cosine of the second angle minus the sine of the first angle, sine of the second angle. I didn't mean to do this in red pen, but that's all right. It is what it is. You got it? Simplify. Cosine alpha is cosine squared alpha, right? You can multiply them. Minus sine squared alpha. All right. So I'll grab my blue pen to indicate that this is the cosine of 2 alpha equals cosine squared alpha minus sine squared alpha. So this is one of the 3 versions of the cosine double alpha formula or identity. So there's 2 more that we're going to look at. And they are built off of the answer that we just got for the cosine of 2 alpha, cosine squared alpha minus sine squared alpha. And they require you to use the Pythagorean identity. 1 equals sine squared alpha plus cosine squared alpha. Remember that one? Okay, so what I'm going to do is I'm going to transfer this information, cosine squared alpha minus sine squared alpha. And what I'd like to do is just put it in one trig expression instead of 2 different ones, sine and cosine. So let's replace cosine squared alpha with 1 minus sine squared alpha. So I really want my highlighter here. I wonder if this is a highlighter. I bet it is. Let me see. Is it? Yes. Okay. So I'm just using a Pythagorean identity there to replace the cosine squared alpha with the 1 minus sine squared alpha minus sine squared alpha. So that's the rest of that statement. Okay, and now let's simplify that. So I can combine these 2 terms, right? Negative sine squared alpha minus sine squared alpha would be negative 2 sine squared alpha. So why would that be useful? I'm going to get my blue pen, and I'm also going to circle that, or put a box around that. So cosine of 2 alpha can also equal 1 minus 2 sine squared alpha, or theta, or x, or whatever the angle is that we're talking about. So that's another version. We're going to find the last one, and then I'll show you why it's interesting to know, or good to know, each version. Okay, so let's take a look at this last one. I'm again going to start with this same equation, that the same expression, cosine squared theta minus sine squared theta. And I'm going to write another version of the double angle for cosine, which looks like, what do you think? What could I replace? Sine squared with 1 minus cosine squared. So I could use the Pythagorean identity again. So we're going to do cosine squared theta minus 1 minus cosine squared theta. And again, that's coming from our Pythagorean identity. So I'm going to go ahead and highlight that I'm replacing that with that. Right, I'll come over here and put Pythag ID, and I'll highlight that in yellow so that you know you can connect those together. Okay, so let's simplify that. We have to distribute first, so we'd have to distribute that minus. So that would be cosine squared theta minus 1 plus cosine squared theta, which we need to simplify a little further because we have some like terms here. That would be 2 cosine squared theta minus 1. And I'm going to grab out my blue pen one more time to indicate that this is another version for the cosine of a double angle. Now, why is it important or why is it useful to know that? So let's say that I give you this information. I tell you that the cosine of theta, 1 theta, not double theta, is equal to 1/2. And I want to know what the cosine of 2 theta is. Which of these 3 formulas would you choose to use so that you could solve for that? I'm going to erase this and get it out of the way. You have the cosine of 1 theta, which is 1/2. And I want to know what is the cosine of double theta. Would you use cosine squared theta minus sine squared theta? 1 minus 2 sine squared theta? Or 2 cosine squared theta minus 1? Yeah, we would use this one because we could say, all right, so that's 2 times cosine theta, which is 1/2 quantity squared minus 1. And I could find the value of the double angle because I have cosine. What if I instead said this? The sine of theta equals 4/5. And I want the cosine of 2 theta. I want it. What are you going to do? So you're going to pick the second one? Is that what you're telling me? So you'd go 1 minus 2 times the sine of theta, which is 4/5 squared. And you would get your double angle. So this is why it's useful to have all of the forms for that. You understand? And that one happens to work out nicely because it's got a Pythagorean identity in it, and so you can manipulate it a bunch of different ways. Okay, moving on to the last one. Tangent of 2 theta. So back to the logic of taking the sum of 2 angles for the tangent of the sum of 2 angles. We can take 2 alpha and split it into alpha plus alpha and use our formula for the tangent of sum of 2 angles, the tangent sum of 2 angles, which would be tangent of the first angle plus tangent of the second angle over 1 minus tangent of the first angle times tangent of the second angle. That's our formula from yesterday. But that's just a lot of extra work. Let's just simplify it. So in your numerator, combine like terms. 2 tangent theta. Not theta, alpha. Over 1 minus tangent theta times tangent theta. Tangent squared, not theta, alpha. What's the matter with me? There we go. So I'm going to grab another color here to indicate, I'll use green here, that the double angle for a tangent of 2 alpha is equal to 2 tangent alpha over 1 minus tangent squared alpha. So what you just experienced is me taking formulas that I already know and deriving new formulas that are maybe more useful when I'm looking for the tangent of a double angle or the sine or the cosine or whatever. Okay, here we go. We have 13 minutes left to do these 2 problems. We can do it. So here we have problems that will be similar to the problems you see tomorrow. Please follow the instructions and read carefully. It says find the exact values, you hear that? Exact, of the sine of 2 theta, or double theta, the cosine of double theta, and the tangent of double theta for the given values of theta. And I've given you, so 1 theta, I'm going to give you 1 theta. The cosine of theta is 3/5. And condition, theta is in quadrant 1. So I will require you for homework to draw a diagram following the conditions. So here's what I know. This is quadrant 1, and in quadrant 1, everything's positive. So I'm going to go ahead and pretty much focus on quadrant 1. And in quadrant 1, everybody's positive. Good to know. Think about that. And here's what I have. I have angle theta. Now remember, angle theta comes from the origin, right? And its terminal side goes somewhere off into quadrant 1, okay? And I have cosine. Cosine of theta, so theta's here somewhere. Cosine of theta is adjacent over hypotenuse. And cosine's your x-axis, yes? All right, so here's what I'm thinking. That my adjacent side of my angle is going to be 3. Now I could do 3/5 and make my hypotenuse 5/5, but I'm just going to expand my unit circle to have a radius of 5 instead of a radius of 1. So this is adjacent over hypotenuse. So I'm going to make my adjacent side or my horizontal side 3 and my hypotenuse 5. And then I'm going to connect the terminal side to the x-axis as proper when I'm on a unit circle or I'm on a coordinate plane. Drop in my right angle and label. This is my adjacent side. This is my hypotenuse. And I'll probably need my opposite side if I want to find the sine of double theta. So there's a number of ways I could go about doing this. I could use my cosine inverse and get a value, but for the angle, but it won't be an exact value. It will be an approximate value. And since we're asked to find exact values, that's not the route to go. So let's identify what's the opposite side of this triangle. Look at the sides I have here. 3 one side, 5 hypotenuse. So what's my other side? It's not square root of 14. It's a 3, 4, 5 right triangle, a Pythagorean triple. And if you need the Pythagorean theorem to help you determine that, you should know the 3, 4, 5. You need to know it if you don't. You just do Pythagorean theorem. 5 squared minus 3 squared equals the opposite side squared. So that's 25, the square root of 25 minus 9, which is square root of 16, which is 4. Okay, so could we close the door real quick? So now that I know that, I want to gather as much information as possible. So let's find the sine of 1 theta. Sine is opposite over hypotenuse, so that is 4/5. And we're also going to have the tangent of double theta, so let's find the tangent of theta. Tangent is opposite over adjacent, which is 3. So 4/3. So now I feel like we've gathered enough information to solve this problem. We have 3 double angles to find. So the sine of 2 theta. Let's get our formulas going. So the sine of 2 theta says this. I'm going to do 2 sine theta cosine theta per our formula that we just derived. And so I'm going to plug in for sine theta. What's sine theta's value? Since I'm looking for exact values, yep, 4/5. Cosine theta is 3/5. And so now I can find the exact value of the sine of 2 theta. Nice to have a calculator around for this. The solution is 24/25. That's an exact value. If you were to find it as a decimal, it'd be one of those ugly decimals that goes on for a long time. There you go. So it's positive. So the sine of 2 theta is positive. Interesting. That means the double angle could be in quadrant 1, or it's possible it could be in quadrant 2. We're going to have to find cosine of double theta to see what happens. So let's do cosine of double theta. So do you want to use, be thoughtful, the first formula, cosine squared theta minus sine squared theta? Or do you want to do 1 minus 2 sine squared theta? Or 2 cosine squared theta minus 1? I don't think so. And here's why. Because that's going to create a fraction on one side of the problem and a whole number on the other, which means then you're going to have to use common denominators. I think it would be easiest to do cosine squared theta minus sine squared theta. But you could use the other one if you want. So what's the cosine of theta? 3/5 squared. And the sine of theta is 4/5 squared. So that's 9/25 minus 16/25, which is negative 7/25. Okay, so that's interesting. So my sine value is positive and my cosine value is negative, which means I'm not in quadrant 1 anymore. I'm in quadrant. So my double angle's in quadrant 2. Yeah, it's like, okay, so here's angle 1 theta. So if I have to do 2 theta, I have to double that. So it's definitely over here somewhere. Okay, that's theta and that's theta. There's 2 theta right there. All right, last one. We got to do a tangent real quick. Here we go. So let's do the tangent of 2 theta. So the formula goes 2 tan theta over 1 minus tan squared theta. So let's plug in tangent. So that's 2 times 4/3 over 1 minus, I'm going to scoot the page up a little bit. Oh, I can't. Yes, I can. There we go. That's as much as I can go, guys. Sorry. 1 minus 4/3 quantity squared. This is where your calculator comes in handy because that's definitely a complex fraction. So we plug that in your calculator and here's what you get. Negative 24/7. So tangent of 2 thetas is negative 24/7. And we know tangent is also negative in quadrant 2. All right, questions about that? You're welcome. Anybody? Okay, the next problem. So here we have the problem where we've been given some values or some conditions. Secant of theta equals negative 3. And theta is between 90 and 180, which means it's in quadrant 2. And we're still under the same instructions where we're finding the sine of 2 theta, the cosine of 2 theta, the tangent of 2 theta. Okay, so what do you consider? Okay, so I'm going to draw my quadrant 2. I'm going to be thoughtful about that. Here's what I know about quadrant 2. Sine is positive. Okay, so that's good to know. What information do we need? Or what other information do we have that's useful? Secant of theta is negative 3. Okay, well, here's what I know. Secant theta is the reciprocal of cosine. So if the secant of theta equals negative 3 over 1, then the cosine of theta equals negative 1 over 3, which is my adjacent and my hypotenuse. Or if I'm in secant, that's my hypotenuse and my adjacent. That's also really useful. Okay, so since I'm in quadrant 2, my cosine or my value of negative 1, that's my adjacent. So this is going to be the measure negative 1 from the origin to the left. Hypotenuse is always positive, so we'll shoot up 3 units and then straight down to the x-axis, put in your right angle. Here's angle theta. Angle theta should be between adjacent and hypotenuse. Okay, so we got cosine. We wrote it down. Cosine of theta is equal to negative 1/3. Let's use a Pythagorean theorem to find this missing side quickly. So should we do 3 squared minus negative 1 squared? Take the square root, right, to find the opposite squared. We just take the square root of that. So that would mean that our opposite side is 2 square roots of 2, because that's the square root of 8, right? 9 minus 1. So this is 2 square root of 2, which allows us then to find the sine of theta, opposite 2 square root of 2 over hypotenuse 3, and the tangent of theta, which is opposite over adjacent. So 2 square root of 2 over 2 square root of 2 over negative 1 which is just negative 2 square root of 2. True? Okay, so let's quickly find the sine of 2 theta. And if you don't mind, I'm not going to write out the formula. I'm just going to plug in values. So it is 2 times the sine, right, which is 2 square root of 2 over 3, times the cosine, negative 1/3. And we're going to simplify that out. 2, let's see, that's negative 4 square root of 2 over 9. And you plug it in your calculator. This is just for your reference. Keep up. Cosine of 2 theta. Again, I'm not going to write out the formula. I'm just going to plug. I'm going to go with the first formula, cosine squared minus sine squared. So that would be negative 1/3 squared minus a sine squared, which would be 2 square root of 2 over 3 quantity squared, which is negative 7/9. And then we're finishing this up before the bell rings. The tangent of 2 theta, plugging that in, would be 2 times tangent of theta, which is 2 square root of 2, negative 2 square root of 2, over 1 minus negative square root of 2 square root of 2 quantity squared. Sorry about that. It took me a second to get there. Doing a little math here, which is negative 4 square root of 2. I'm going to simplify here in a second. Over negative 7. Let's finish it out. It's 4 square root of 2 over 7. Thank you. So your homework is on Canvas, problems 2 and 4. Thank you for the lovely message over here. Have a good day.